Complex numbers. You guys gonna learn how to work with complex numbers today. Some of the basic operations, how to find distances, how it applies to vectors, and then next class we will work on a little bit more of applications, I guess you could say, of complex numbers. So all the basic stuff today. First off, to start, any number that's in the form of a plus bi, where a and b are elements of real numbers, and I is the square root of -1, it is called a complex number. Okay, you guys dealt with complex numbers back in algebra 2, right? Maybe a little bit, maybe just some basic operation stuff. I mean, you guys do know that when you take the square root of a negative number, it does produce an imaginary number. Okay, so we got a little bit of that. But the general form of any complex number is written as so is z equals a plus bi, where a is the real part of z, sometimes written as REZ, and b is the imaginary part of z, which is written as IMZ. Okay, so these are different types of notations in which you can see this complex number written. Every complex number has a complex conjugate. Conjugate, does that word sound familiar? Yes. Okay, so yes, it's still here. The notation for the conjugate is represented with an asterisk, okay, and the exponent of z, and that's essentially where you reverse the sign of the imaginary part. So if your complex number is -3 plus 4i, then its conjugate would be -3 minus 4i, okay? But every complex number has a pair. Oof. All right, so I need to make sure y'all know about I, okay? This is where, like I said, I'm under the impression that y'all would have done imaginary numbers back in algebra 2, because back when I taught algebra 2, that's when you guys learned it. It's been a while, but that was when it should have been. So right now these just look like regular things, but let me add some symbols, okay? So if you had to take the square root of 81, this is a pretty simple one. You know, you pretty much just treat it as the square root of -1 times the square root of 81, which would just be what? 9i, okay? Just treat it as normal. Okay, here, let me add in the radical symbol. What would that be?
Well, square root 3, like a -I square root.
So yes, -I square root of 3. Very good. This negative comes from the negatives on the outside. The I comes from the -1 that's on the inside. Very good. How would I solve this? And get
X equals y.
Thank you. Don't forget, anytime you take the square root of both sides, you get plus or minus 2i. And then can you solve this quadratic for me over here, please? Everyone solve this quadratic?
The quadratic formula?
Quadratic formula, walk me through it.
It's, you want me to say the formula or the?
With the stuff plugged in.
-1 plus or minus the square root of -7/2.
Very good, because remember it's that b squared minus 4ac underneath, but we do need to simplify that -7 underneath the root. So then it's just going to be what?
I square root of 7.
Yes, I square root of 7 over 2. Okay. And actually, notation wise, usually the I comes after a number. Just for notation wise, or you can write it separately as -1/2 plus or minus 7 over 2i. Either one will be acceptable. Did I miss something?
Yeah.
Oh, did she say square root of 7? I missed it. Yeah, that was my mistake. Oh, yes. Okay, okay. Sorry. I've been that hesitant. All right. Good. So we're good there. Do you guys remember how to factor something like a² minus b²?
Plus b a minus.
That's right, a plus b, a minus b, good old difference of perfect squares, but how do you factor a squared plus b squared? It involves imaginary numbers very similarly. It's one's a plus, one's a minus, but this time, since it's a sum, you know you're going to end up with an imaginary number. So it's actually a plus bi and a minus bi. That's actually how you factor the sum of two squares. Okay. So if you have something like this, of course, I know that I can subtract over 3, divide by 2, and take the square root. But I'm going to emphasize the whole factoring concept here. This one here can be solved through factoring. Okay, you essentially take the square root of your first term, square root of your second term. When I take the square root of 2x squared, what am I left with? Huh? X root 2. And then over here, the square root of 3 is just as, so then you have the square root of 3i minus the square root of 3i, and that's technically how you would factor this. Since you are asked to solve, again, this is just another way to kind of emphasize the whole factoring of the sum between two squares. And so just take the square root, make sure you include an I after the B, and then from there you can set both factors equal to 0 and solve respectively for X. Okay, so then if I continue to solve both of these, I'm going to swing over here. So I don't have that much space. I will have x root 2 equals a negative root, dropping all the roots today, y'all. Negative root 3i, or negative I root 3, divide both sides by the square root of 2. I'll fix it here. Negative I root 3 over the square root of 2. Can I have a square in the denominator? How do I make it out of the denominator? I have to rationalize. So what's the square root of 2 times the square root of 2? So the bottom is 2, but the top becomes negative I root 6. Very good. So that was for the positive one. The negative one would be similar. So it'll be I root 6 over 2. It's the same.
So when we're factoring out something like that, which isn't a full quadratic in itself, like where it has the A, B, and the C, it's okay to just square root both and then add the I to the C.
Yeah, to the back end. Because remember, if I fold it out, I will get 2x squared plus 3. Operations of complex numbers. Do not write all this down. Okay? Do not write all this down. But essentially, this is what you are doing. Okay? When you have two complex numbers that you have to perform any type of operations with, when it's addition, you essentially are adding the reals and then adding the imaginaries. Okay? That's all you're doing. When you're subtracting, you subtract the reals, subtract the imaginaries. When you multiply, yes, you do old school FOIL or distributed property. A times C, A times DI, BI times C, and BI times DI. You'll get BDI squared. What does I squared equal? Negative 1. So technically, this just turns to a negative BD. Don't forget about that. Okay. When you're dividing, you can't have any imaginary parts in your denominator. So you always multiply by the conjugate, the top and bottom, so you can get only real numbers in the denominator, just like how you can have a square root in the denominator, similar. Okay. We rationalize the denominator when the square root's involved. We essentially multiply by the conjugate, so we don't have any imaginaries in the denominator. So let's take a look at this example. It says if we have this complex number 3 plus 2i, and we have another complex number that is 4 minus I, We want to find z plus w, z minus w, z times w, and then z divided by w, okay? Again, when you add or subtract, you add the real part and add the imaginary part, or you subtract the real, subtract the imaginary. Multiplication, you FOIL. Division, make sure there's no imaginary in your denominator, okay? Give you 5 minutes to do A, B, C, and D. So what'd you get when you did z plus w? What? Z minus w. Very good. Order does matter when you're adding and when you're subtracting. Order does matter. When you multiply, what did you get? Yes? Okay, good. Remember, you FOIL, so that'd be 12 minus 3i plus 8i minus 2i squared. Remember, I squared is equal to a -1, so you essentially have a +2, a 5i, and then a 12. Very good. When you divide it, you had to do the conjugate, yes? Just, so I should have an answer that does not have any imaginary numbers in the denominator. What'd you get? Over what? Very, very good. What was the conjugate of w? 4 plus I. Good. Questions? Now, two complex numbers are equal if their real parts are equal and their imaginary parts are equal. Okay, so keep that in mind when you are potentially having to find different variables in equations, such as this one. It says find x and y such that x plus yi times 2 minus I is equal to -I. That means on the left, everything on the left should equal everything on the right. So one way you could do this, is you could FOIL out that parenthesis to get 2x minus xi plus 2yi minus yi squared. I'm looking for a value for x and y, okay? What is the real part on the left-hand side? 2x and a plus y, because that I squared turns into a -1. Negative y times -1 is a positive y. So that means that 2x plus y should equal my real part on the left-hand side. What's the real part on the left? I mean, on the right-hand side. What's the real part on the right-hand side? 0. And then that means that the imaginary part on the left-hand side, which is this -x plus 2y times I, should equal -I. Or essentially, if I drop the i's, it should just equal what? -1. How do I solve this? Substitution or elimination, okay? I want to choose elimination because if I just multiply this second expression or equation by a +2, Jesus, I'm struggling today, y'all. I'll be able to cancel out my x's. So if I multiply the second equation by 2, I'll end up getting -2x plus 4y is equal to a -2. My x's cancel out. I have 5y is equal to -2. So y is equal to -2/5. How do I find the x value? I can plug it into either one. I'm gonna go ahead and use this since I have space underneath. 2 times -2/5 is a -4/5. I'm gonna add 4/5 over. That's gonna give me a -1/5. So x is equal to a +1/5. Another way I could have solved this was I could have divided from the very beginning both sides by 2 minus I, and then gotten rid of did the conjugate, and then kind of lined up the real parts with the imaginary parts. I could have done that as well. want you guys to try the next one on your own. What we get? 3 and -1. Very good. FOIL to equal. Wonderful. Few rules for complex conjugate. Very good to know. Some of them should be kind of just straightforward. If you have the conjugate and it's being raised as conjugate, you just get the original. Okay. So again, remember the asterisk means the conjugate. If you have two complex numbers being added and you're asked to take the conjugate, well, essentially that means you just add the conjugates of Z1 and Z2. If you're subtracting 2 and you're asked to do the conjugate, well, that's just doing nothing but taking the conjugate of one, subtracting from the conjugate of the other. You see how the other ones go as well. When you multiply two complex numbers and you want the conjugate, you essentially just multiply the two conjugates together. Division, divide the conjugates. It's the same thing whether you raise a complex number to a power and then apply the conjugate, just like it would be to take the conjugate and apply it to that same power for all positive integers of n. And realize that the sum between the original and its conjugate and the product between the original and the conjugate are real, always. Okay. Questions? Okay, so we're going to show that for all complex numbers Z1 and Z2. We're going to show this right here. Okay, it's a little proof. All right. So let's talk about our complex number. Z1. What is the general makeup of complex number in general? A plus bi. Okay, so that will represent Z1. I have a different complex number. How can I represent that? D is my real. I mean, C is my real, D is my imaginary. So I'm trying to show that Z1 plus Z2, the sum of that to the conjugate is going to be the right-hand side. I just need to do a little bit of work. Okay. So let me add Z1 plus Z2 together. When I add them together, what do I get? They're not conjugates of each other. How would I add these? A plus C. Huh? Exactly. Like if A, B, C, and D were numbers, this is essentially what I would do, right? I would add the reals, add the imaginaries, and attach the I on the back of the imaginary, right? So now I want the conjugate. Of those, right? What's the conjugate of Z1? What would it be? A minus BI. And what about the conjugate of Z2? So then when I add those together, what do I get? I still get A plus C. I'll have a minus B. Well, I'll have this, but how would I work with this part here?
Can you take out a negative I?
I can take out a negative I, which leaves me with what on the inside? So I'll have A plus C minus B plus D I. which is essentially that, what we wrote first, okay? And so if anything, I probably should have, let's switch these. This is the proof. And look at what you have. You have A minus BI plus C minus DI. Isn't that the conjugate of Z1 plus the conjugate of Z2? So essentially this right-hand side, not necessarily looking at the equals part, the right-hand side essentially will represent your proof, your show. Questions on some of the basics, complex numbers?
Okay, so when you have so all three are three different equations, aren't they?
What is?
What you had actually,
Mm-hmm.
all three of them are three different equations. Where did they come from again? That one.
This one here came from the inside part. Like I took the left-hand side of this equation, and I was essentially showing that it equaled the right-hand side. So I started off by adding Z1 and Z2 together. Then I applied the conjugate, which is these two. Distribute the negative, rearranged, and then we had the conjugate of Z1 plus the conjugate of Z2. Complex numbers, like I was explaining before, off camera, was that they can be graphed on a complex plane, also known as an Argand plane, very similar to a traditional Cartesian plane. The only difference is that your horizontal axis is your real number line, where all of your real numbers lie, and your vertical axis is your purely imaginary numbers, okay? X is called, again, your real axis, your y-axis is called your imaginary axis. Any numbers, any complex numbers that have a real and imaginary part will lie within the quadrants 1, 2, 3, and 4. It works the same way, okay? These are all your positive reals. These are all your negative reals, positive imaginary, negative imaginary, okay? So it works the same way like a regular coordinate, all right? So like A, comma, B, I, works like a regular coordinate, all right?
There's no A, back, it's just I to make this be on the left.
Exactly, so if it was for I only, then that would be here on your y-axis or imaginary axis. And since I drew it like that, it's good for you guys to know that any point on a Cartesian plane can be represented by a vector. So do you realize, remember position vector is OP, O representing your origin, P representing initially the point. That vector can be translated into complex numbers, okay? So anytime you do see a vector such as 2, 3, this can be represented as 2 plus 3i inside of your real and imaginary axes. And so I have a few examples on the next page, just to make sure you guys are good with that. Anything in standard position always has a initial point at the origin. The terminal point is actually wherever the end is, so essentially where that coordinate is, what that complex number is. So if you look here, OP represents the vector 2, 3, or 2 plus 3i. OQ, 4 minus I. OR basically negative 3i. Again, anything that's purely imaginary lies on the vertical axis. Anything that's purely real lies on the horizontal axis. Vector OS, that's negative 3 minus I. Okay, so again, you can use that, make the correlation between vectors and complex numbers. One thing you guys do need to realize is that complex conjugate is a reflection over the real axis, because if you think about it, if I have 1 plus 2i, its conjugate would be 1 minus 2i. So then that would exist here for the original, then here for its conjugate. Okay, it's a reflection over that real axis. Just a few common things. So hopefully you guys saw how I graphed that. I went 1 unit over to the right on my real, 2 units up for my imaginary. Okay, essentially 1, 2, and then 1, negative 2. Just like you would graph any point. Okay. So I'm going to use that as well as refresh your memory on vectors, because once we get through like this last little bit, I got to go back over some vector stuff. So it's actually really good. Suppose Z1 is equal to 4 plus I and Z2 is equal to negative 1 plus 2I. We're going to find both results algebraically and using vectors. If you guys could help me out and do the algebraic part first, I'll come in and do the vector part. Okay, so I want you to do A, B, and C algebraically. Tell me what the result of these are, and then I'll come through with the vectors. So what's Z1 plus Z2? Okay, so what does that mean? Well, if you take it back to vectors, right? This is our real, this is our imaginary. Remember vectors, we did this. Oh gosh, I'm so rusty. Z1 will be 4 plus I, so I'll go 4 over on the real, 1 up on my imaginary, and I will have this vector right here that will represent Z1, okay? Now Z2 would technically be negative 1, 2I, but if you recall from the 2 different ways that we did sum of vectors was triangular and parallelogram. Triangular method came from the end. One vector started where the other one ended. So if I started here to make vector Z2, then I would technically go over 1 and up 2, which will put me right there. And that is actually exactly where 3 plus 3I would lie. Because I'm 3 over on the real axis, 3 up on the imaginary. And there's our triangular method. Okay. So we can also do this using vectors. Remember when we add triangular method, the result, the initial point is the start of one vector, the terminal point is the end of the second vector. What you guys get for B? 2 minus 3I? 6 minus 3I? Don't forget, like scalar multiplication, I have to multiply Z2 by, I could say negative 2, so then I'd be 2 minus 4I. I'm going to add that to 4 plus I, and that's how we get a 6 minus 3I. How you would graph that, right, too big for this. Technically, this would be that vector that represents the Z minus 2, Z2. So I have 4 plus I. Here's Z1. Then I have technically 2 minus 4I. So 2 minus 4I would essentially put me here. But I can go from the end and I can go over 2, down 4, and that puts me right there. And that is negative 2 Z2. The little triangular method. What you guys get for 2z1 plus z2 conjugate? 7. This one was a nice one. Okay. Remember, that means it just was going to lie here. That's the result. Okay. But I can also get that from doing 2z1, which would have been 8 plus 2i. So go all the way to 8, 2i, which would be this point here. And then plus z2, which was a -1 plus 2i. So again, here, conjugate. Thank you. So then it would have been a -1 minus 2i. So that would have took me here. Technically going back over 1 down 2, which puts me right at the end. Thank you for that. And I know y'all probably can't see this because I'm using almost like the same color as the thing. So either vectors or algebra, or it's both ways.
We'll probably have to show vectors on the exam.
Possibly they merge the two concepts together.
I'm gonna bet my money on it.
Maybe. I mean, there's a lot of topics, a lot of material to cover within the certain number of marks that y'all have.
Find the area of the triangle
For a vector that you have to create the triangle for, and you have to find the angle between the two vectors in order to find the angle that goes into the formula. Oh, I can see it now. Since complex numbers can be represented with vectors, you can also find magnitude and direction as well. Throw back to vectors, you guys. Remember, magnitude was technically the size of the vector. It's called a modulus for a complex number. Direction, it's called an argument for a complex number. It can be abbreviated as ARGZ. That's the way it can be abbreviated. These were our two formulas that we did back when we did vectors. They have not changed. Magnitude is still represented with those like absolute value looking bars, and it's still the square root of a squared plus b squared. And to find the direction, we did a tangent of theta equals b over a. It has not changed. It's still the same. It's just now, instead of it being like those two values within the component form, it's the real and the imaginary of the complex number. A few properties that I should have had you guys write down that can be helpful. I'm going to write them down by hand on the next slide after you guys get this. Here's a few properties, okay? These vertical bars represent the modulus, okay? So when you do the modulus of this of your complex conjugate, it's the same as when you do the modulus of your complex number. When you square your modulus, that's essentially taking your complex number and its conjugate and multiplying them together. You have two complex numbers, and you're asked to find the modulus, aka magnitude squared a squared plus b squared. It's the same thing as saying the magnitude of one times the magnitude of the other, or the modulus of your first complex number times the modulus of your second complex number. Same applies with division. And last but not least, you raise your complex number to a power. It's essentially like taking your modulus of the complex number and raising it to that power. Yes. Remember, we're talking about size, length, magnitude. One more stipulation. Go back and add it. One more thing, I forgot, theta here with complex numbers are bounded between negative pi and positive pi. That's very important. So if we go about finding the direction of the complex number, of that perspective vector, we want to make sure that our theta is in between negative pi and positive pi. Okay. So let's take a look at an example. Okay, almost through. We're going to find the modulus z for all of these, and the ARGZ, which is stands for the argument, aka the direction for z, for each of these. Now, what you should notice is that they're all very similar. So when we find the modulus of this one, it's going to be 1 squared plus 3 squared, which is equal to what? Square root of 10. It's going to be similar to the modulus here for this one because my A is -1, my B is 3, but when I square and add, it's still going to give me square root of 10. And then for C, even though the order is changed, -3 squared plus a -1 squared is still going to be square root of 10. So even though the modulus is the same for all of these, there is a distinct difference between each one of these complex numbers. What is it? It's going to be the direction. What quadrant in the origin plane is 1 of plus 3i? The first quadrant. So when it comes to finding the argument for z, remember this is your real and this is your imaginary. This is z. Your angle is going to be acute, okay? It's going to be in between 0 and pi over 2 radians. So to find the argument, I'm going to do the tangent theta of b over a, or in other words, the tangent inverse of 3. Can you guys do this in your calculator, radian mode? Tell me what I get. Good luck. See, pi over 2 is 1.4 something. So I know we're going to be getting the decimal here because that is not on our unit circle.
1.24.
1.25. That's not going to be my angle. It's going to be my argument. Okay. And B, what quadrant am I in? Yep, the second. Because my real is negative and my imaginary is positive. So the angle I'm going to be looking for, this one here. Okay. So again, tangent theta is equal to B over A. So theta is going to equal the tangent inverse of -3. What do you get? Can you do that? -1.25? Okay, that doesn't make sense because it's supposed to be in the second quadrant. Remember, for theta, I'm bounded in between negative pi and positive pi. And it should be in the second quadrant. So how do I get this actual angle here? What do you think I'm gonna have to do? So we'll go back to, it's not the opposite, because I actually have to go back to pre-cal. I should have to go back to pre-cal. Well, it can't go back to pre-cal. Huh? Now subtract 2 pi. You are kind of thinking around the right path when it comes to you're giving me coterminal angles, not coterminal, but reference angles. Y'all remember reference angles? When it's in the second quadrant, you do pi minus the angle that you actually got. Or if you want, the angle you actually found was this one. And I know it's a terrible drawing, actually, let me fix that. It's like the one that's directly across from it. So I could just add pi to that answer. And the reason why is because I want the angle that's in the second quadrant, not the fourth. What is that? And that is bigger than pi over 2, so that is theta. So kind of keep that in mind. The quadrants are, you know, they could be kind of funky. And the reason why this is because when you do the inverse of tangent, you're actually bounded between negative pi over 2 and pi over 2. So it's not going to give you anything outside of that. So you have to do a little bit of alteration to get there. What about negative 3 minus I?
Oh, what quadrant?
Yeah,
3.
third quadrant. So negative 3 on my real, negative 1 on my imaginary. So my angle for theta is actually going to be clockwise or counterclockwise? Is it going to be like the first two? It's going to be clockwise because it's greater than pi. And remember, we're bounded between negative pi and positive pi. So if I went clockwise, I'd be past pi and I don't want that. So my angle for theta has got to be less than 0. So then this is going to be tangent theta equals b over a. So that's negative 1 over negative 3, or essentially the tangent inverse of 1/3. Tangent inverse of 1/3.
It's 0.322.
So that actually gives me this angle right here.
So subtracting pi, you get negative 2.80.
And that's theta. Because think about it. Huh?
You can have a negative. I thought the whole point was that. Okay.
No, you can't have a negative as long as it's in between negative pi and positive pi. So negative 3.14 to positive 3.14. That's what our argument always has to be. It has to be in between those two values. That's why it's important to know what quadrant we're in. So our numbers need to make sense. Our angles need to make sense. All right, let's look at this. We're gonna find the modulus of z given this information. Definitely get this one down. This was a little bit different. Gotta do a little bit of work for this. Okay. So essentially we have to take this expression here and we basically have to get modulus z by itself. Okay. Easiest way to do that is we got to get rid of the modulus. Remember, modulus is like the square root of a squared plus b squared. So how do you get rid of the square root? You square it. It's going to be the same thing that we're going to do here. We're going to square both sides. Now, when I square this, 3 squared, of course, becomes 9. And using your properties of moduluses, when you square a modulus, what do you get? Oh. Z times the conjugate of z. So z essentially is that z plus 1. And then the conjugate is going to be z conjugate plus 1. That 1 essentially is like just a regular constant. It's not like a real part or imaginary part. So really and truly, the complex number is z. And so that 1 is just kind of gets dragged along with it because it's within the modulus. So then it'll be equal to z times its conjugate, which would be z conjugate plus 9. What do you think I should do from here? FOIL. So I'm gonna leave the 9 out for a moment. That gives me z conjugate plus z conjugate plus 1. On the right, z conjugate plus 9z conjugate plus 81. I'm going to distribute over that 9 now. Remember, what I'm trying to do is I am trying to find modulus z. Granted, yes, I did get rid of my moduluses at this point, but I can actually bring them back in. I just have to do a little bit of work. From this point, what do you think I could do? I sure can. Like, I wanted to get them on the same side. They would cancel out. So those are gone. Can I do anything else? So maybe move this over. That would give me a z conjugate. What about the 9 and the 81? Huh? So I'll subtract the 9 over to get 72. So this equals 72. Then what can I do? Divide by 8. So z and z conjugate equal 9. And what do z conjugate equal? That z conjugate equals the modulus of z squared. So I can replace that. And then to get rid of the squared, I would. And now I just have modulus z is equal to 3. That's using your properties of modulus. Modulus is one line I did skip. The reason why we were able to make this possible, it was an accident, to be honest. I should have done this because this is the proper way to apply that property. Because it's technically z conjugate, but when you have z plus 1 conjugate, that's the same thing as what we had there. So it's like I skipped that step. Doesn't change anything. We're okay? Last example. All this is kind of covering like some basic things that are good to know. Because then we're going to get kind of more into the applications that deal with like polar form and Euler form and the Morse theorem, all that with complex numbers. So if Z1 is equivalent to OP1 and Z2 is equivalent to OP2, and the modulus of Z1 minus Z2 is the distance between points P1 and P2. Because remember, OP is that vector in standard position. So the length between them would essentially be the distance between those 2 points. So in an example, P is 2, 3, and Q is 6, 1. They're 2 points on a Cartesian plane. We're going to use complex numbers to find the distance of PQ and the midpoint of PQ. We're going to use complex numbers. Of course, we could always use the distance formula, old school midpoint formula, but we're using complex numbers here. Okay? So if I were to transfer these into vectors, what would OP be? Oh, okay. 2, 3. And then OQ would be that's essentially what you have. So to find the distance between the two, we essentially need this right here. We need that complex number that represents that situation. How do I find that complex number? Or in other words, how do I find that vector? Do y'all remember how to do this?
OQ minus OP.
It'll be OQ minus OP. Okay, so throw it back to vectors. Remember, anytime we were given 2 points and we're trying to find the vector that's between them, we would do the last point minus the first point, or in this case, that vector minus that vector. So then what is that when we subtract? 4, 2. So 4, 2 is the vector, which means 4 plus 2i would be the complex number. That's equivalent to that. So the distance of PQ is the same thing as saying the modulus of that vector, which would be what? What's the formula? Square root of a squared plus b squared. What's 4 squared plus 2 squared? Square root of 20. How's that simplify?
2, 5.
So then that'll be my distance. That'll be my modulus of that respective complex number, 4 plus 2i. Midpoint, using complex numbers, is we would take essentially the complex number for P, the complex number for Q, which was 2 plus 3i and 6 plus I, P and Q. And we actually would do old school midpoint formula with it. Okay? I add my reals, add my imaginaries, and then divide by 2. So what's 8? Well, 6 plus 2 plus 3i plus I divided by 2 going to be?
4 plus 1.
So my midpoint is going to be 4. No, it's 4 plus 2i, yes, but the point itself would be 4, 2. That's some basics with complex numbers.